Hi everyone, welcome to the season finale of Astronomy on Tap here again virtually. But as almost our whole season has been virtually up to now, it's a fitting end to this season to come to you from our computers to your computers. Today we are having one fabulous talk by Dr. Taissa Danilovic, who will tell us what molecules can tell us about dying stars. And then afterwards, we will play science or fiction. And for those of you who have already been with us for the January event, you might have an idea what is coming up. For all the others, just let yourselves be surprised. So as you can see here on the announcement, it says 29th of June. You probably realize today is not the 29th of June, but we actually changed our date to today, transposed the event by a week. You might know why there was a football game last week. I'm not going to talk any more about this football game. I think a lot of us try to, forget about it. But anyway, here we are today. And as always, you can contact us on Facebook, here on YouTube. You can follow us on Twitter, Instagram. You can always write an email to us. We are very happy to also answer all astronomy-related questions. And today, in our event, please interact with us in the chat. The chat is the way to talk to us, and we can answer all the questions that you put in the chat over in our video call. And also, interacting in the chat is really, really important today because we are going to play science or fiction. So how does it work? Well, later on, after the first talk, you will see several of our AOT members, and they will try to convince you of some scientific facts. So you will see them here on the screen, and they will talk, and one of them will tell you the truth, and one of you will tell you a lie, and you need to decide which of these is the truth and which of these is the lie. So, first of all, the first step, find out who of these people tells the truth. Then you can tell us in the chat which one of those is the truth and which one of these is the lie. And finally, once you've told us these, we will pick some winners from the people who have answered, and these people will win some awesome prizes. Some examples of which you can see over here. So we hope you have a lot of fun playing this. And before we play this, though, we'll first start with our first talk. So I'll hand the microphone over to Felix and our first speaker.
Felix, your moderator for today, which is mostly the case. The last time I gave a talk, and so David took over for me. So I will guide you today through our talk as well as our event that Laila already mentioned to you. So we are at our season finale, and we are still virtual, as you can see. Of course, maybe after the summer break, we can return to the pub, which we really hope we can do. So stay tuned. So let's just jump right into it. So we have our first talk today, which is by Taissa Danilovic. She is originally from Melbourne, Australia, and she did her PhD at Chalmers University of Technology and the Onsala Space Observatory in Sweden, which she finished in 2016. She then moved to the Katholieke Universiteit in Leuven in Belgium, where she is now a senior postdoctoral fellow. And there she studies molecules around evolved stars to learn more about the fates of stars similar to our sun. So welcome, Taissa, to the show.
Thank you, Felix.
So I see you're already sharing your slides, so you're free to start whenever.
Hey, great, thanks. So as Felix has said, today I'll be talking about what molecules can tell us about dying stars. But first, let's talk about what exactly I mean by dying stars. So this is the sun. This is the star that we are all most familiar with. It's a pretty average star. In our galaxy, there are a lot of other stars like it. And the sun has been shining, as we can experience on many days, for about 5 billion years. And we expect it to keep shining for about another 5 billion years. So right now, what's happening inside the star, in the core of the sun, is that hydrogen is being fused, and these fusion reactions are creating a lot of energy, and this is causing the sun to shine. But in about 5 billion years, it will run out of hydrogen, and then it will start to change. So what are some of these changes? Well, after burning hydrogen, it can spend a bit of time fusing helium, and that will also cause it to shine, but also cause it to expand. And eventually it will run out of anything that it can burn in its core, and it will become what we call an AGB star. So starting from the sun in the bottom left-hand corner, it will end up being much larger. So the expanded edge of the AGB star will be probably a little bit bigger than the orbit of the Earth around the sun. So it will really have grown a lot. And because the fusion reactions in the core have stopped, there are only unstable fusion reactions happening in a few sort of thin shells around the core. So still inside the star, of course, but not in the center anymore, a bit further out. And these are unstable, and they cause the star to pulsate. So that means it gets bigger and smaller over time. The pulsations cause the star to throw off its outer layers. And this happens throughout the life of the AGB star, and eventually it will throw off all of its outer layers and become what we call a planetary nebula, like is pictured on the right here. Now, a planetary nebula actually has nothing to do with planets, aside from the fact that it's around a star, or it will be around the leftover core of this star. The reason it's called a planetary nebula is actually because it's a bit bluish. It was discovered, the idea of planetary nebulas were discovered by William Herschel, who also discovered the planet Uranus, and he thought they kind of looked similar because they were, bluish. Otherwise, they don't really have anything in common. Now, I'm going to zoom in on this planetary nebula. Well, show you a different image of the same one. This is called the Helix Nebula. And what we're actually seeing in this image is what we call visible light. So this is the same kind of light that we can see with our stars, with our eyes around this star. In this particular case, what we're seeing is light reflected off dust that was formed around the star as it was dying. And now it's been ejected all the way, and it's still moving outwards from the center of the star. And eventually it will sort of move even further outwards and join what we call the interstellar medium, which is the gaps between stars. So this is interesting. We want to understand how this whole process works, because stars like this are depositing a lot of gas and dust, especially dust, but also enriched elements that were created inside the star and have now been ejected and are free in the universe to be used for future stars, planets, asteroids, etc. So we want to understand how this process works, because stars like this are responsible for a significant amount of the dust that we end up having in the universe. So maybe about half, depending on exactly who you ask. And they're also responsible for at least half of the carbon. So that's quite important to us as carbon-based life forms, and other heavier elements as well. So I mentioned that this image is in optical light, but in astronomy, we want to use all the possible tools available to us, and we want to look at light at all different wavelengths. So here is a nice diagram from the European Space Agency, ESA, showing all or most of their space telescopes. And down the bottom here is a spectrum showing the progression from the longest wavelengths on the left, so radio microwaves, submillimeter, to the shortest wavelengths on the right, in this case ending at gamma rays. So optical light is the light that we can see with our eyes, but not the only light that we want to use to explore the universe. So the kind of light that I mostly work with, or mostly study, is in this range here, shown by this arrow. So I mostly work in the submillimeter and microwave regime, which are types of radio waves, but also a little bit in the infrared. So of all these telescopes shown here, Herschel is the one that I've used in the past. So Herschel was observing in the submillimeter in space, where the observations weren't blocked by the Earth's atmosphere. And also in this regime, there's the JWST, which hasn't launched yet, but hopefully will soon. That one's more in the infrared, but is still useful for us when we want to study molecules in space, generally speaking. Now, the Herschel Space Telescope was very useful, but it had a relatively short life and is no longer running. Basically, it ran out of coolant. It was never meant to last forever. So for the time being, we've been mainly using telescopes on Earth. One of the benefits of this is that we can build a much larger radio dish on Earth than we can put into space very easily. So Herschel, the dish of Herschel, is actually about 3 meters across. Some of the telescopes I've worked with more recently are much bigger. So Apex, which is in Chile, has a 12-meter dish. So that's a lot bigger. And IRAM, which is in Spain, has a 30-meter dish. So I've said bigger is better, but I haven't really explained why. So there are 2 reasons that we want bigger telescopes. So first, a bigger dish catches more light just because it is literally bigger. And this makes it more sensitive, so we can look at fainter signals coming from space. The bigger dish also gives us a higher resolution. What this means is we can see smaller things in space or further away. So if we want to really study these less common molecules, for example, or very distant galaxies and so forth, we really want to try to use bigger telescopes to do that. So here's another example of a larger telescope, which is the Effelsburg in Germany, and that's a 100-meter dish, so that's already quite a bit bigger. And I will say it's technologically challenging to build bigger telescopes. I mean, this telescope, this is kind of the size of a trailer, and you can see a car in this picture. And then here, there's I think that's a bus in the image. So it's really getting a lot bigger, and that's also a technological challenge. Until a few years ago, the largest telescope, a radio telescope, was the Arecibo 305-meter dish. And this was so big that it actually couldn't move. It had to wait for the Earth's rotation to change which sky was above it. That was, great for a while, but unfortunately, things went a bit wrong and it broke, and it turned out it was quite difficult to fix, and unfortunately broke even more. An alternative to building one very large dish is what we call an interferometer. So this is a lot of smaller telescopes that work together as though they were one giant telescope. So in this image, this is a side-on view of ALMA and some of the ALMA dishes, which are very similar in size. Well, in fact, the same size as the Apex dish I showed earlier, just a slightly different model. And so ALMA is made up of 66 antennas. So each of these dishes is called an antenna, and they can be spaced up to 16 kilometers apart. And by working together, they can act as though they're a telescope that's like 16 kilometers in diameter, which of course is much bigger than we can actually build. Here's another image of ALMA from above, which gives you a bit of an idea of how the telescopes are spread out. But this is slightly more than half of them, so not the one that's far away being the 16 kilometer baseline. So I've told you how or what instruments we use to look at things in space, but now I'll tell you a bit more about what we're looking at, why we're looking at it, how we can even see molecules in space. So on Earth, molecules are all around us. So the air we breathe is made up of relatively simple molecules. The water is a molecule in liquid form. Most of our food is on some level molecular. So molecules are really small, you can't see them, right? You can't see the air, you can't see individual particles in water. So if they're so small, how can we see them in space when they're really far away? Well, the answer to that is how these molecules, especially the simpler molecules made up of a few atoms each only, it's how they interact with radiation. And then that radiation, so that light, we can collect with our telescopes. Here is a picture, excuse me, of a fairly simple molecule. This is carbon monoxide. You don't really want to encounter it on Earth, but there is a lot of it out in space because both carbon and oxygen are quite common. Now, you can see this molecule is not perfectly symmetric because the carbon atom is a bit larger than the oxygen atom. And what that means is when it rotates, well, rather, it rotates in a particular way so that when light interacts with it, we can see that light either being absorbed or emitted. Because of what I'll say is the quantum nature of reality, only very specific wavelengths of light can interact with any particular molecule. So we have a specific wavelength of light causing the molecule to spin, and then another specific wavelength of light causing the molecule to spin, twice as fast, and so forth. And this is what we can observe using our telescopes from Earth. Now, what wavelengths of light we're interested in for any particular molecule depends on the molecule itself. So I showed you this quite simple molecule of carbon monoxide. Here is a very slightly more complicated molecule, ammonia. And as you can see, it's not two atoms in a line, it's four atoms making a funny sort of triangle shape. And ammonia can rotate in more different unique ways, right? There's only one way you can spin carbon monoxide. It's symmetric, or it's the same if you spin it in different directions. It's the same amount of energy to spin it. But here we have a few axes of rotation that are different. And that means that we get different, what we call rotational energy levels. So that's the energy that we need to make it rotate, which comes from the light. And through this, we can identify that whatever frequencies we see might belong to ammonia instead of belonging to carbon monoxide. Another very popular molecule is water. There's actually a lot of water in space. It's very common. Oxygen is a very common element. Hydrogen is the most common element, so we end up with a lot of water. Possibly not a lot of water on Mars, but everywhere else in the universe, there is a lot of water. This molecule being a V shape also can rotate in different ways. And as I've said before, we can use that to understand what we're looking at. And of course, an Astronomy on Tap talk would not be complete if I didn't also show the ethanol molecule, which has also been detected in space, as actually a lot more methanol than ethanol in space. So a little bit harder to find the ethanol, and probably don't drink the space methanol, but it's still out there, and it's thematically relevant.
It also looks very cute, I would say.
Yes, it looks a bit like a little dog or something. I always
yes.
So I've talked about how we can identify what frequency of light belongs to which molecule. So in practice, we use perhaps a telescope like Herschel, and I've used Herschel as the example here because I've also mentioned water, which is very hard to observe from the ground, from the Earth, because there's a lot of water in the atmosphere, which blocks out the water that we could see in space. It gets in the way, basically. But the telescope will give us something that looks a bit like this, so a bunch of squiggly lines. But, as astronomers, we can learn to understand these lines and identify them and say, okay, well, they belong to these molecules. And then we can use our more complicated tools to analyze how much of each molecule there is, like where is it near this star that we're looking at? What does this tell us? So this is the kind of thing we get from Herschel, or from what I call single dish telescopes, which, like the name sounds, is just individual radio dishes looking at stars or whatever else they're looking at. But I mentioned ALMA before, and I can't do this talk without showing this very iconic image of, this is an AGB star, or rather carbon monoxide around an AGB star. This was observed with ALMA. And when I say ALMA has a very large spatial resolution, I mean, this allows us to see this sort of pattern. With one of those single dishes, we wouldn't be able to see this. We would just get that spectrum. We would not be able to distinguish any of this structure. So it's really exciting to be able to see this kind of structure. So I said before, carbon monoxide is one of the most common molecules, and it's used to find structures around these stars. And also it's used for us to be able to tell how quickly the stars are ejecting their outer layers. Now, this particular star is what we call, excuse me, what we call a carbon star. And the reason it was being observed when this observation was made was because this circle around the outside, we already knew more or less that it was there, not maybe exactly where it was, but we knew it existed because it's a signature of when the star basically went through an episode of very strong ejection of its outer layers. So normally there's a sort of a steady state kind of thing going on, but every few thousand years, or maybe 10,000 years, there's a bigger eruption, and we call it a thermal pulse, and it creates this sort of shell. So we're expecting to see a shell. What we weren't expecting to see is this spiral pattern that you can see forming around the star. And what that tells us is that the mass loss, the ejected outer layers of the star, this isn't happening in a sort of smooth, uniform way, which was what we always assumed before we could look at these things more clearly. It's actually telling us that, well, it's making a spiral. Why is it making a spiral? And the best answer we have so far is that there's some sort of small companion. So I say small because it can't be a bright star, because we would have already seen it. But either a small star or a large planet is orbiting this AGB star and causing the material that it's ejecting to be funneled into this spiral shape, basically. So this already tells us a lot more about this star than we knew before we could see it in this lovely high resolution. And since then, this was actually published in Nature in 2012. A project I'm involved with, the Atomium project, has observed several AGB stars using ALMA and found all sorts of patterns around them. We did not choose, well, some of the stars we thought there'd be something interesting. Some of the stars we chose because they were convenient and we wanted to see what we would see. And the answer was lots of interesting shapes. So you can see there's some spirals along the bottom here. This lovely star here is some sort of rose petal pattern. This star on the side here is a bit of an hourglass. Now, it's a bit hard to tell, but this one's also an hourglass, just a bit bigger than fits in the box that we observed with. So we found all these exciting new patterns, and actually what causes them, probably more planets, like leftover planets, maybe stellar companions for some of the more extreme shapes. So maybe there is another star orbiting, and yeah, I mean, it can cause these unusual shapes.
Are these colors different molecules?
Oh, yes. Yes, thank you for reminding me. So this is all still carbon monoxide, but what the different colors are indicating is that the red stuff is moving away from us, and the blue stuff is moving towards us, and the white stuff is, well, not moving relative to the star. So yeah, that also gives us an idea of, this hourglass is actually like a three-dimensional hourglass. It's not a flat 2D shape. So I've shown you a lot of nice pictures of carbon monoxide because it does lend itself the most to making nice pictures, but we can learn from other molecules as well. So from carbon monoxide, we mainly want to learn about how quickly this matter is being ejected, which tells us how long these stars will spend dying. Right, so once they become AGB stars, how long will they be AGB stars? How much stuff will they eject into the interstellar medium? And that tells us about how much gas and dust in the interstellar medium will be available for the next generation of stars and planets, and how much, what the extent of the influence these stars will have on the galaxy as well. I'm personally interested in the chemical reactions that happen around dying stars. So what other molecules do we see? How do they interact with each other? And one of the main reasons for studying this is to understand how and what kind of dust forms around these stars, because this dust also goes on to form, as I keep saying, future stars and planets and so forth. And the dust is really the thing that will survive in the same or a very similar form after it leaves the star. And as I mentioned earlier, we also get heavier elements, some of which probably are also incorporated into dust. And we just want to understand, how they end up in the future stars and planets, etc. So I hope you found that interesting, and thank you for listening.
Thank you very much, Taissa. That was very comprehensive. And I actually also learned some new things today. So in the chat, please feel free to ask questions. Don't be shy. You must have a lot of questions, I'm sure. Otherwise, I might ask a question. This is maybe a common one. So hydrogen is the most abundant element, right? So can we also observe, or why don't we observe molecular hydrogen?
It's possible, but it's difficult, is the short answer. We can't very easily observe it from Earth because of the frequencies involved. So actually, molecular hydrogen is just two hydrogens stuck together. And because it's symmetric, the two hydrogens are the same, it doesn't actually interact rotationally with light. We have to rely on it vibrating, interacting vibrationally with light, so moving apart. But the frequencies at which that happen are much higher and more difficult to see from Earth.
Yeah, and for these higher frequencies, you really have to go to space, right?
Yes, we can see atomic hydrogen, so just hydrogen by itself, or ionized hydrogen a bit more easily. But that's not really what we see around these types of stars. We expect most of it to be molecular hydrogen.
And then you see, you can use the space telescope like Herschel, right? How long did that run actually? You mentioned that it does not work anymore.
I think it ran longer than they expected it to, but it was still only something like 4 years, I think. It certainly died during my PhD, I remember that.
Yeah, that's always unfortunate when you're relying on some data, right?
Yes, well, we actually got more data than we were expecting.
Yeah.
So in the end, it was fine.
Yeah, mostly people have more data than they can actually analyze.
Especially now with ALMA. Yes.
Yeah. We actually have a question now from the chat. They're asking, which is the biggest, most complicated molecule? I guess they're referring to the ones that we can observe in space or have observed in space.
So that's a tricky question, especially it depends on what you mean by most complicated. I can answer the biggest a bit more easily, which is C60. So it's called a buckyball. It's sort of like a soccer ball, football shape made out of carbon. That has been detected in space. The way that has to be detected is slightly different. So that's 60 carbon atoms in a ball. So that's quite large. On more complicated, as in more different atoms or more different elements involved, I think we've certainly seen largish molecules with like 3 or 4 different elements that are formed mainly out of carbon, but then with something like nitrogen, oxygen, sulfur, and hydrogen also attached. So a few of those complicated molecules, either longish carbon chains, although then we normally still only have a few elements, or maybe simple rings have been detected. You might have seen in the news, well, a few years ago now, a simple sugar was detected. Yeah.
I guess at some point the names of the molecules also get quite complicated, right? So
yes,
and the sugar is already pretty interesting, pretty large molecule.
Yes, well, it's less. Sorry, I've forgotten the name of the sugar molecule exactly, but it wasn't sucrose. It was less complicated than that. It was not a circle, not a ring. It was just like a line of molecules, but I think it's one of these artificial sweetener type sugars.
Okay, so then thank you very much again, Taissa, for the really great talk. And then we move on to our next part of our event today, which is the long-awaited return of our fact or fiction format. And today this will replace our normal quiz. But you can still participate and should participate in this fact or fiction quiz. And yeah, you have to guess the correct answer of some of very interesting questions that we selected for you. So I will now ask our contestants on the virtual stage. So I will explain again shortly how this will work. So in the following, I will ask several questions where two of you at a time will give their respective answers. So one will be true, but the other will be false. And you have 1 minute each to present your arguments. And I will take your time and stop you also relentlessly at the minute mark. So you have to take that into account. And you as audience should really interact with us in the chat by guessing the correct answer of the two. We will we give you a bit of time after the answers, not too much, so you can think while people are talking. And please provide your guess in the chat, as we will raffle prizes among the participants in the chat, so it doesn't matter if you were right or wrong. So just put your best guess on who is correct. So we are now going to witness the most anticipated match in the history of astronomy on tap. From the former capital city of Germany in Bonn, ladies and gentlemen, let's get ready to rumble. Unfortunately, we couldn't get Michael Buffer to do that, so I had to do it. And we will just start with our first question, where we have our contestants, Sandra versus Maud. I see they are both here. And now let me make sure that my timer is ready. Okay, so the question is, does your location on Earth influence the lunar phase that you see? And Sandra, you will start, and you have 1 minute starting from now.
Thank you, Felix. So the answer is obviously yes. How we see the moon does depend on the location of the Earth, and I've brought a small moon here for you. And as you hopefully can see, or maybe you know that already, if it's shaped like this, so if the belly is here, if it looks like an A, it's what we call a waning moon, and if it's the other side, it's a waxing moon, right? So now that it's easier for you to see, I prepared a little experiment. If we are on the northern hemisphere and when you see the moon like this, so, the A-shaped one, and it's fine. But if we are on the equator, and now I rotate this for you, for how someone on the equator would see that, the moon would look like it's curved upwards, right? So maybe you've seen it already in some movies, like 1001 Night. And if it's on the southern hemisphere, now I rotate it again for you, wait, like this. then it's exactly.
Unfortunately, the time was up. So I guess you made your point. And okay, resetting my timer. The second answer will come from Maud. So you have 1 minute.
Hello, everyone. So the phase of the moon does not depend on where you are on Earth. We're going to call phase how much of the moon is in the light and how much is in the shadow. So imagine this is the moon and the face is red, okay? The moon is always showing the same face to us. I am the Earth, my head, and you will be the sun. So the moon is orbiting the Earth, always showing the same red face, you see. Okay, it's not easy to see, but always showing the same face. And how much light will the moon receive only depend on you, the sun. So if the moon is here, the sun will hit like that. And if it's there, it will be hit differently by the sun. So that's why our position on Earth does not matter, because what changes the phase of the moon is the position of the moon compared to the sun, and not the position.
Okay, so the time was up there, but I guess we were almost done. Okay, I will give you just a few seconds to think about what you just heard. And then we will reveal to you who's telling the truth and who's telling a blatant lie. Okay, I guess you had enough time to think about it. So let us reveal the answer to you. Yes, you put on your crowns for true and false. So we will now reveal to you why Sandra was false.
Yeah, so I just tried to divert your awareness to something that is actually true but has nothing to do with the topic. So yes, depending on where you stand on Earth, the moon will appear differently, but it has nothing to do with what the phase of the moon, like it's a growing ball or one that goes smaller. That nothing to do with that. So I tried to say something true, which is logical, to confuse you, and I hope some of you were confused. And of course, what Maud said is totally correct, and I just tried to lie.
So there was some truth in the lie, yes, but Maud was indeed correct here. Okay, so let us move on to our second question, where we have again 2 contestants, and this time it will be Sven versus David. So both are on stage, and I will now ask the question. The same goes again, 1 minute for each of you. And what happens when astronauts burp in 0 gravity? And so Sven, please start with your answer. You have 1 minute.
Okay, so that's actually quite dangerous, and more dangerous than you might think, because like in space, there's no gravity and there are not many air currents, so the air you breathe and exhale stays around you. That is actually why, for example, astronauts, when they sleep, have to keep a fan pointed at their face, because otherwise they suffocate from, well, their own exhaled carbon dioxide. And so when you burp, you actually exhale a lot of carbon dioxide. So I mean, it's while you're on the ISS, it's not really a problem. When you burp, you just move away. But when you do a spacewalk and you're in the confined environment of your spacesuit, then it's actually really dangerous. So in 2013, there was actually an incident where Luca Parmitano, a NASA astronaut, was like, he was burping so much that he almost suffocated, and they had to do an emergency retreat to the ISS to save him from, well, suffocating from his own burps. I'm done.
Okay, you were right on time, Sven. And okay, let's hear our second answer from David. So please go ahead.
Well, The down-to-earth answer is that astronauts are not able to burp in microgravity. The simple reason behind this fact is that you need some gas near your gullet in your digestive tract if you want to burp. On Earth, gravity kindly helps us with the phase separation in our digestive tract, pulling down the dense liquid and paste while pushing the light gas towards the gullet. This gas can be used to burp. But when you live on the International Space Station, the phases in your stomach won't be separated that nicely. If you try to burp in zero gravity, you may actually end up vomiting. So say a big thank you to gravity for helping us with our digestion on Earth.
Okay, this time we were both on time, and you gave your answers about the important topic of burping in space. And we will now reveal who of you was correct and who was not. After, I guess, people had enough time to think, right? Yeah, probably. Lies.
Yeah.
So, yeah, so let's hear why, Sven, you gave a blatant lie.
I mean, yeah, David was correct. So I guess there's not that much to say. Most of what I said was true. There is the danger of suffocation in your sleep when you don't keep a fan pointed at your face, and the same probably also would happen if you burp, but you're just not able to. And the astronaut that almost suffocated, that was due to a water leak and not due to burping. So yeah.
And it's interesting that you brought up that story. That made it really credible, I think. I could almost believe it. Okay. Then we will go on to the next question, where we have now Sandra and David. Both are here on stage, ready to fight. Well, with words, of course. And the question is, when does Earth reach the point where it is closest to the sun? So now, Sandra, start with your minute of arguments.
So the answer is it's in January. This year it was on January the 2nd, and next year it will be on January the 4th. And that depends a bit on how the other planets move around us, and especially our moon. So why is this fact not intuitive to you? Because it doesn't matter to life on Earth at all. We live 150 million kilometers away from the sun, and it's only a difference of 5 million. That's 3%. That's like if I would be a couple of centimeters taller, it just doesn't matter. What people usually get confused with is with the seasons. We think if we're closer, it's warmer. But you can disable this fact quite easily, because then there would be summer on the whole globe at the same time. And as you probably know, in Australia, it's currently winter. So that's not what it can be. The answer is it's January when we're closest to the sun.
Okay, thank you, Sandra. That was on time.
And correct.
That is for the audience to decide. Well, I mean, they can guess. So we will have our second answer now from David. So please go ahead.
In fact, it's slightly more complicated than the rubbish Sandra told you. The truth is, our planet Earth comes close to the sun twice a year, in January and in July. According to Kepler's first law of celestial mechanics, planetary orbits are elliptical, with the sun in the middle of the orbit. Since the sun is so massive, it makes perfect sense that it is placed in the center of any orbit. To illustrate why Earth approaches the sun twice a year, I made a simple sketch. You see the elliptic orbit with the happy sun sitting in the very center of the system. You easily understand that there are two perihelia and two aphelia, so 2 points where we are close and 2 points where we are far from the sun. But as Sandra already told you correctly, this is completely unrelated to the seasons.
Unfortunately, I had to mute you there, David. You are over time, but you had the minute to make your point. So I will give the audience now a few seconds, a bit of time to guess who is correct and who is not. I think they're both pretty confident. Yeah, drawing. So please provide your guess in the chat. And I guess you now had enough time to think about it, not Google it. And so we will reveal who is right. There they are, the true and false crowds. Okay, so David, explain to us why you were false.
Yeah, the thing is, the sun is placed in the focus of the elliptic orbit. And this is why there's only one perihelion. And it's actually in January when we are close. This is why the winter on the northern hemisphere is slightly less strong than on the southern hemisphere, or the other way around. But anyway, Sandra was correct.
I told you.
I guess you both thought that you're correct. So thanks for that clarification, David.
But you can't actually explain the existence of Carnival by this model.
The carnival? What does that have?
In the fifth season.
Ah, I see what you did there. Okay, let us move on to the next question. So, our contestants, please come on stage. And now we have again Maud and Sven on stage. So, and rules are the same as always. And we have Sven starting with the answer to the question, why do stars twinkle? So Sven, please go ahead.
So the reason stars twinkle is actually the same reason we put telescopes in space. I mean, it would be much, much easier to construct telescopes on the ground, and we also do that a lot, but we also send them up in space. And that is because our atmosphere is not perfectly transparent. We have some slight air currents in the atmosphere. And they slightly change the way that the light reaches Earth. It's very, very tiny effect, but due to the fact that stars are this tiny effect actually makes a big impact there, because the light bundles that come from stars and reach our eyes are very, very tiny. So as soon as they are refracted a little bit different by the atmosphere, they change their properties just a little bit, and that is why the light from the stars that reaches us always changes just a little bit with time. That is just because we have air currents in the atmosphere, and yeah, that's the reason stars twinkle.
Okay, just at the minute mark to stop there. So perfect on time. And we have a different answer given by Maud. So please go ahead and start now.
Yeah, so there is many reasons why stars twinkle. Of course, the atmosphere, like Sven just told you, but there is also a lot of things in space, especially a lot of gas, a lot of dust, and all of those cataclysmic events like supernovae that produce a lot of very high speed gas movements, sometimes even relativistic. So all of that actually make star twinkle. There is also all the junk between the star and us. That was
Okay.
short, sorry.
Yeah, I mean, it's fine. as long as you don't go over time, it's fine. So we have these two answers now. So please provide your best guess in the chat. It'd be really nice to have like some Jeopardy thinking music now. Can we play that? Well, I guess we don't have a technician that can do that right now, right? Just imagine it in your head while you're thinking.
Smells like copyright infringement to me.
Yeah, we don't want our video to be removed due to copyright claims. So just think about it. So I'll give you just a few more seconds. And okay, I guess that is enough. So let us reveal the answers. Yes, there you have it. So just explain to us, Maud, why it was false what you told us.
Yeah, so it's exactly as Sven told you. The telescope argument is actually a really good image. So the twinkling is only due to the atmosphere. My argument was a bit misleading because there is indeed stuff in space, but the dust would just absorb the light and re-emit it into another wavelength, so usually infrared. So it's something totally different. And the reason why stars twinkle is because they're really small and really far away. So turbulence in the atmosphere is going to change the light we are receiving. While with planets, for example, they're much bigger. So the light path is coming from a bigger surface, which means that there is less chance that all the light will get disturbed by the same atmospheric turbulence as for a dot star far away. I hope that was clear.
That's actually a very good point. I should have made that.
No, your argument with the telescope was really good.
Yeah, I hope all make sense now to you in the audience. I do have to say that space weather can actually mess up observations as well. But for the reason that stars twinkle, it's actually the Earth's atmosphere. Okay, so we have a few more questions for you. So let's move on. Now I ask on stage David and Maud again. Now you two will have your match of the day. And the question this time is, do black holes have negative mass? And this time we will start with David. So please go ahead.
The correct answer is yes. Recall, mass and energy are equivalent according to Einstein's famous equation E equals mc squared. So whatever holds true for energy is also true for mass. You may also know that for potential energy, the absolute value doesn't matter and can be chosen freely. It's only the difference between two energy values that matters in physics. This is the same for mass due to the equivalence of mass and energy. Now, let's analyze the mass density distribution in the observable universe like cosmologists often do. By convention, they subtract the average density. As explained before, this has no effect on the physics, but apparently those regions are where the density is below the average have a negative density, which corresponds to a negative mass, and these regions are better known as black holes. Now you know.
Okay, thank you, David. That was also exactly at the minute mark. And yeah, you can decide if that is true or not after hearing the second answer, which comes from Maud. So please go ahead.
Yes, let us remember how black holes are formed and where they come from. So they come from a very massive star that is going to collapse and become really small and very dense. So that's why black holes have a positive mass, because they're coming from something already very massive. And as David told you, indeed, you can think about black hole distorting the space-time. So if you have something with a positive mass distorting space-time, you will see a a potential well, like you always see on images. If black hole had a negative mass, you would see something like that. The space-time would be distorted up and not creating a hole like that. So yeah, that's my explanation.
Okay, you were also good in time. Okay, so now you can think about if actually black holes do have negative mass or not, judging from the answers that you just got. I think they were both very convincing. So, but only one is true. So just type your answer in the chat, and remember participation to your prize. So please do not be shy. Also, guessing wrong is not a bad thing, because I think everyone is very convincing here.
David has a much cooler display. That's cheating.
I don't think it will convince anybody.
You know, in the audience, you should be convinced by the facts, of course, and not by anything else. So I guess you had enough time to think. So let us reveal the correct answer to you. Yes, so black holes indeed have no negative mass. So why were you false? Just explain yourself, David.
Yeah, I just combined some facts and some bullshit, and it turned out to be completely nonsense, what I argued. Actually, a negative mass might push things apart. And yeah, what black holes do is they eat a lot of matter. So Maud was totally correct.
Yeah, in fact, negative mass it's not really observed so far, I think. So yeah, Maud was correct. Okay, let us move on to the next question, where we have two different contestants again. Sven and Sandra, please come on stage. Yeah, you are ready, I see it. Okay, so let me ask the question that you both have to answer now. And the question is, where did the Big Bang take place? So Sven will start with his answer. Please go ahead.
Yeah, so the name Big Bang is actually quite misleading, because it implies that there was an explosion or something, which didn't happen. So what we now believe is the following. So Edwin Hubble discovered that almost all galaxies are receding from us, and they're actually moving away faster the further they are away. So there are two possible explanations. One is we are the center of the entire universe, and we are the center of the explosion, and everything is just moving away from the explosion, or everything is moving away from everything. And when you spin that backwards, that means if you go backwards in time, everything is moving closer and closer together. And so there has to be a time where actually the distance between each point in the universe was zero. And so the entire universe was compressed in a point with zero extent, and that is called the Big Bang. But we don't really know what actually happened there.
Yes, again, right on time. Yeah, you practice being on time very well, I guess.
No, I have a timer running on the meantime.
Yeah, you have your timer yourself. So yeah, you don't want to run into me muting you. I see that. Okay. I know it's very scary. So Sandra, now I hope that you will also be on time. And if not, I have to mute you. But please go ahead with your answer now.
Yeah, so space and time is a concept, is nothing that can be created. And I just want to repeat first argument of Sven, Big Bang didn't happen. I mean, but I will continue further. So there's some origin of the universe, and we just have to find it. Like we have also searching for the age of the universe, right? And as Sven already said, almost all galaxies drift apart from each other. And the Earth is part of that flow, which is clearly imprinted on the microwave sky. You see a brighter direction where we move into, a dimmer direction where we came from. And if we trace all this back, of course, everything will collapse to one point, and we just, as part of the cosmological research, have to find that place and that time when it happened. And it's not that easy, but the direction is clear. Yeah, so that's all I have to say. Space is a concept, and the Big Bang did happen.
Okay, you were in fact in time. So it's interesting to hear the cosmologists talk about cosmology. And the thing is, only one of you is correct for this question. So you have to guess, who is it? One has like a Playmobil figure, I guess it was. Did that convince you? You should, of course, you should be convinced by the facts. And you have to guess. Now, who is correct? And I give you just a few more seconds to think about it. And I guess, yeah. Now, he's like in a quantum state now where he is both false and true. The same as Sandra. And now when we observe it, you actually see the quantum state that they are in. Okay, as we can see, Sandra is false. So what did you tell us there? Why was it false?
Yeah, first of all, I have to apologize. Since I made my PhD here in the cosmology department, I really cringed in the inside, because this is one of the most common misconceptions about the Big Bang. Actually, that was my outright lie. So with the Big Bang, time started to tick, and with the Big Bang, space started to exist. And since all the space, you can imagine, was compressed, as soon as you expanded, all the space was part of this Big Bang. So I mixed some wrong arguments, that are in themselves facts for my claims. So just at the wrong point, I put them here. And of course, Sven didn't say the Big Bang didn't happen. He just said it's not an explosion. And I just ripped part of that argument out of what he said and tried to convince you that he's bullshitting around.
So if cosmologist ever doesn't happen, maybe lawyer would be you're very good at twisting my words.
You made it easy.
Actually, I don't know really who defined the term Big Bang, because I mean it is actually misleading, right? But I guess that just happens in science, and we are there for you to clarify this. So now you know which is correct. Okay. So we have sort of a bonus or advanced question for you that is a bit more in depth. And there we have, again, two contestants, which are Maud and Sven. Sven wants to show that he's already false. No. Actually, we still don't know yet. We haven't observed your quantum state of true and false yet. So the question is, how do astronomers define probability? And we have two answers. So Maud, you start. So please go ahead.
Yes, so first, the frequentist approach is to say that you would define probability as the number of occurrence of one event in many trials. And this is the only correct way to define probability, of course. I mean, if I ask you what is the probability to get a 5 if you launch a dice, you would just launch the dice many times and count how many times you got a 5 and how many times you got everything else, basically. We do exactly the same in astrophysics. So if you want, for example, to see an exoplanet transiting in front of a star, you would just look at the light of the star being diminishing by the exoplanet passing in front. and you would just take that measurement many, many times to know that this is indeed an exoplanet orbiting around a star and not just a random event, because that could be an asteroid passing by.
Okay, that was the minute mark. Okay, we have another answer from Sven. So please tell us your arguments. Go ahead.
So yeah, the way astronomers define probability is the Bayesian way. And that is that with a probability, you mean your personal belief that something will happen. So to take Maud's argument, when you roll a dice and you say the probability of me rolling a 5 is 1 in 6, then it means that you believe that this chance that to roll the 5 will happen in 1 in 6 times. And the reason we do that is that this is a more convenient way to work with probabilities, because with this we can also take in prior knowledge that we know from other experiments into our data. So what we can do is we take some other experiment and already take their constraints, their knowledge about cosmology, and combine them with our experiment to get better knowledge about our cosmological model and to get a better understanding of the universe.
Okay, I guess I was muting you before you spoke the last word of your sentence there, and yeah, the minute was over. So you can guess again now who is like telling the truth about how astronomers define probability. It's a bit of more complicated concept, but I think you can get it. So just provide your guess in the chat. So yes, just think about probability is actually a very interesting concept. I don't know about many people dislike statistics in math class, but I actually always liked it. So it's a very interesting concept to think about. Okay, so I think you had enough time to think. So let us reveal now the truth. Now that's a surprise. How can both of you be correct? But in fact, it is true. It says in this case, there's not a uniquely correct way to define probability. Maud, do you want to say anything else about the frequentist approach?
Not really, I guess. So it's a very interesting debate. In case you have never heard of frequentist and Bayesian, you can watch video on YouTube. It's a really, really interesting scientific debate. I personally think that the frequentist approach is the most natural one, at least for me. I guess that's the easiest to understand. And I always find the Bayesian one to be like the smart choice, because you would actually, like Sven said, take into account prior knowledge of, okay, maybe you know that your data will behave a certain way. So that's why we often use it in astrophysics. Also, the problem of the frequentist approach in astrophysics is that you cannot most of the time take a lot of measurement for something. For example, for the transit of the exoplanet in front of a star, we cannot take like 100 measurements of that. That would cost enormous amount of money to monopolize a telescope to take 100 measurements of only one little exoplanet around one star. So I guess that's why the frequentist approach is maybe not always used in astrophysics, because yeah, it's difficult to do the same experiment many times.
Yeah, that is true. Actually, the ball that you have that's very versatile, right? It has been a moon and a black hole and a planet, right? So
yes, it's actually from Köln Carnival. So we are sponsored today from the Rot Grün, I don't know their name, but something like that.
Yeah, the 5th season, we already explained that today, why it's why is that the case. Yeah, okay, Sven, you can also like tell us something more about the Bayesian approach if you want.
I mean, Maud was explaining all the major points. In the end, it doesn't really make much of a difference in most cases. Like the thing that really just changes is your interpretation of the results. So your methods are very, very similar, and yeah, it's just how you view the concept of probability itself. And yeah, the major difference is that with Bayesian statistics, you can actually implement prior knowledge. And that's why actually in cosmology, we are mostly favoring that. But yeah, as Maud said, the frequentist approach might be the more intuitive one. So it's really an active debate, and there's nothing settled, I guess.
Okay, so now there you have it. How probably maybe you know now a bit better how probability works. And yeah, that has been our fact or fiction event for today. So I hope you liked it, and maybe we will do it again, hopefully in the pub. Yeah, our contestants can come on stage again. So thanks a lot to all the contestants, because they took a lot of time to prepare all these answers for you and tried to mislead you, or actually told you the truth. So yeah, I hope you had a lot of fun. I certainly did. And then now I will say goodbye and hand over to Laila again.
Yeah, thank you very much. Thank you very much. That was a lot of fun, and I learned a lot, and I was almost fooled by a couple of you. And yeah, just because the question arose earlier, there was the question who actually coined the term Big Bang. That was actually Fred Hoyle. Fred Hoyle was an astronomer who did not believe in the Big Bang, and because he didn't believe in the Big Bang, he wanted to give it a ridiculous name, and this is where the name comes from. So it's actually a feature that the name is so ridiculous. So thank you all. Thank you all for joining. Thank you all for joining our season finale. Now, the only thing I want to leave you with is, because this is our season finale, I would like to thank everyone of the team and everyone of our audience members who stayed with us during the virtual times, during all the virtual events. Thank you to all the team that helped prepare those events, and we hope that they went as smoothly as those virtual events happen. But we really, really, really hope that when we are back in September, probably, that we will be back in the pub. We want to take pictures like the one that you see here on the slide, and we really want to welcome you all back to Fiddlers. So with that, I wish you all a very, very nice summer. And yeah, so, and also the winner for the fact or fiction right now will be posted into the chat, and I would like to ask the winner to contact us on our email address. Our email address is aotbonn@gmail.com, so we can get in touch with you regarding the prize. So thank you very much all. Have a great summer, and see you in the